Excellent. Thanks so much for coming, everybody, tonight. So I think we have a super exciting meetup tonight, including some very big announcements. But before we get started, we are being hosted here by a wonderful traditional organization. Traditional, but very innovative as well. So a few words from Christoph.
So thank you, everybody, for being here today. I'm very proud to have such good speakers here today. Just a few words before we start. As you said, we are a traditional company, but we're a spin-off of Commerzbank. So we are quite young. We are like a startup. We were just founded in January this year. So as you can see, quite young. What we're doing here is to help the corporates in Germany with the digitization. And as you can imagine, this is a huge issue for them. Everybody knows the word disruption, and it was, I think, the buzzword for the last few years. But actually, this is what, for the corporates, is the most, or the biggest problem. So how could they handle this challenge? I think it's quite difficult for them. And to give them a little advice, to help them, we created this open space here to make them, to give them possibilities to face these challenges. But we're more than that. The corporates are, they are just the one column we have. The second column are startups. As we think, startups and the corporates, they have to network more. They have to work closer together. And this is why we created also kind of an accelerator here, where we help startups, international and national startups, to get access to our client base of Commerzbank. And if you're B2B startups, this should be quite amazing, as you have access to, we're about 65,000 corporates we have as clients. And I think this is a very good point to start if you're, for example, from America and you want to start your new B2B business, you get really directly access. So if you're a startup here or you know one who want to come to Germany, just give me a hint or just give me a notice and we can talk about that. So that's, I think, enough from open space now, and I'm really happy to give over to you now. Thank you for being here today.
Thanks so much. So we have two talks today. First of all, we have a talk about Cosmos, and then we have a talk about Polkadot. Now, you're going to see some t-shirts lying around, and you can take some of those if you really want them. But also what you're going to notice on those t-shirts is that on both of them it says Internet of Blockchain. So obviously there's something connecting these projects, and I want to talk just a few minutes about what that is. And when Bitcoin started, and later when Ethereum started, there was very much this idea that there was going to be one blockchain that was going to manage all these applications, everything, the whole financial system was going to be on Bitcoin, and then Ethereum was going to handle everything. And I think today it's become very clear that that's not the case. Instead, we have many blockchains that have different characteristics, they're managed by different people, different interests, and they're not really interoperable. And so what needs to happen for this industry and this technology to really reach its full potential is that it needs to be possible for those projects to interoperate, for value to be moved between chains, for true scalability to be achieved, for applications on one chain to be able to call functions on other chains. So on all of those ideas, I think we can look at as the Internet of Blockchain idea. And so we're also announcing today that we're going to launch a foundation called the Interchain Foundation, which is going to support those projects, fund those projects, and make those projects possible, with the two first ones being Cosmos and Polkadot. So Cosmos, of course, you're going to hear much more about this, is about the token transfer between blockchains and between different blockchains that can also be managed by different people and have very different control structures. And on the other hand, Polkadot allows to have a trust-free messaging between blockchains that can have different characteristics, but that have a sort of a shared security basis. So they solve like different aspects to this problem and different aspects that make possible the Internet of Blockchain. Now, before we go into those two talks, I also want to give briefly to Wendell and Thomas from Omise, because they are big supporters of both of those projects, and I think they have a different perspective as well, because they're building applications today that want to leverage exactly what is being built by these projects. So yeah, thanks so much for coming, everybody. I hope you are going to be as excited as I am about what's happening here, and yeah.
Hi, everybody. So this event actually it may be very, very special, and I hope that it's one of the first of these kinds of events that, that leads to a sequence of many, many of these kinds of events. At Omise, we're working on a number of different projects, and over the last year and a half, we have been working on supporting a lot of projects, particularly in the Ethereum space. And you know, one thing we're noticing as a company looking to use some of this technology is that it's becoming more and more, in a way, esoteric and specialized. And the number of people that are aware of a given project seem to get smaller and smaller. And the number of people that understand them even smaller still. So clearly there was a problem, right? It's like we're all kind of yelling out in smaller and smaller echo chambers. But the Internet of Blockchain concept itself is a very, very powerful thing. It's something that, if you really think about it, it makes complete sense. You know, eventually we'll have networks where not only public and private chains, but massively distinct, interesting networks can communicate with each other, exchange value with each other. And we think this is one of the most important things to seeing this stuff really, really adopted. In fact, the Internet of Blockchains is probably the key to unlocking this great potential of this technology that we've all been so excited for a very long time. And so that's why we'll be supporting both of these projects going forward. And Thomas wanted to say a few words as well, because he has a kind of personal view on it.
Hello, I'm Thomas from Omise, and one of the things that, first a little background. Omise is a payments company operating in Asia Pacific. Our offices are currently in Thailand, Japan, Singapore, and Indonesia, and this year we will also be expanding to more countries in the region. And we are a white label payments solution for many businesses, but we also do a lot of back-end and infrastructure for financial institutions. And we see that there is a lot of people in the area, hundreds of millions actually, that are left out of the digital economy because they cannot access financial services. So we have just launched our new project called Omise Go, which is targeted specifically at unbanked or unbankable people as part of our financial inclusion attempt to integrate with them and the existing online economy. As Joseph Poon, the inventor of Lightning Network, said one time to me, financial inclusion is not about being served the goods, it's about serving the goods yourself. And so for this reason, at Omise, the Omise Go platform, which is an open source and white label e-wallet platform designed to be used by the existing closed e-wallet and other digital money silos that exist, many of which exist throughout Asia. It is designed to give the financial inclusion by two factors that align with the original Nakamoto vision, Satoshi Nakamoto vision. The first is that the network that processes financial transactions, these are mainstream financial transactions, should ideally be run by independent validators, the way that Bitcoin was intended, one CPU, one vote. So we are looking to see how this can be done in a proof-of-stake way. The second, and this is where Internet of Blockchains idea becomes very, very strong, is that we aim to see decentralized currencies, so network-backed currencies, not fiat currencies, run side by side with FBTs, fiat-backed tokens, so like collateralized national money, in mobile applications that are accessible to mainstream users. So we plan to implement Satoshi's original vision, but in these two separate streams that will come together, and we will talk about this in more detail over the next few months when we talk about our roadmap. Also, yeah, we have a token sale, I guess, just announced at EdCon, and we will be supporting as much as possible, because Cosmos and Polkadot are very possibly the two technologies that will make our vision of responsible payment service and financial business through financial inclusion and consideration of the people that we are serving, and inclusion of them, not just in the economy, not just in the way that they have access to resources through equitable resource distribution, but also in the way that they are part of the means of production, that they can be involved, or that there can be a wide variety of people, not necessarily end user, it doesn't necessarily have to be the same, but that many people can be involved in securing the network to prevent any kind of industry or technology capture by a special interest, even if it is Omise itself. We are very committed to decentralization in a real way, and so thank you very much to have us here today.
Should I introduce the? You want to? Yeah. Oh, okay. So Jay, come on up. Here he comes. Do you have a microphone stand? Do you have a stand?
Yeah, it's okay.
All right, let's see if this is. Is your projector auto detecting?
Awesome. Hello. Hi. So, really glad to be here, and I'm going to be talking about Cosmos. So, a little short story on how this came to be. I started working on Tendermint, which is an open source blockchain engine. It started in 2014, and it started because I read somewhere on an internet forum somebody complaining about how proof of work needs to be improved, or that we need to move away from proof of work because of environmental factors. So that piqued my interest, and I started looking at it, and I discovered not only environmental issues, but also scalability issues and speed issues. So I realized, okay, this may be a real problem. If we can find a way to solve the proof of stake or nothing at stake problem, then it seems like this ecosystem can really blossom. I think I was lucky to find a BFT, Byzantine fault tolerance, research papers one day, and when I read this one paper, everything started to click, and we've been working on developing Tendermint ever since. So Cosmos is a network of blockchains powered by classical or traditional Byzantine fault-tolerant algorithms as the consensus layer. And of course, it can also connect to existing proof-of-work systems. Maybe we'll get into that today. But let me start off by telling you a little more about Tendermint. So this is what happened. I started reading consensus papers like the FOP impossibility result, published in 1985. The person here, Professor Lynch, also wrote another paper 3 years later called Consensus in the Presence of Partial Synchrony. It was published in 1988. And so this was, I think, one of the first or the first solutions to the Byzantine fault-tolerant problem in a non-synchronous setting, meaning like in the internet setting. And it has all the pieces that you need to build a consensus engine for a blockchain. Of course, many people know about PBFT. Hyperledger, for example, implements PBFT. That was published in 1999, and it was the first algorithm to have continuous consensus. So it was much more like a blockchain than the previous paper. But still, nobody really cared because nobody had thought, what the application of such a system could be until 2008, when Satoshi Nakamoto published the Bitcoin white paper. That became the first widely distributed, widely deployed Byzantine fault-tolerant consensus system. But maybe now it's time to look back and try to bring back the BFT algorithms for blockchains. So Tendermint is like I said, it's a blockchain engine or a consensus engine. It works for both public and private chains. So when it was first created, it was, if you read the old white paper, it's about a proof-of-stake chain. But since then, it's been modified a bit, and it is agnostic to whether it's a proof-of-stake system or a permission system. It works for any system. So if you look at the diagrams here below, you'll see that it sits in between, the hardware and the application logic and how that chain is administered. So it's a kind of middleware. And it can work for a permission system where you need to be a member of a consortium to validate, or it can work in a public system where if you have a staking token or enough collateral, then you can validate. Validate just means signing and securing the blockchain and creating and committing new blocks. So a validator is just a proof-of-work miner without the proof-of-work. A little background here. So the way this works, it doesn't use proof of work. It uses public-private key cryptography and signing. So it's as if you imagine all of us here in this room and we want to come to consensus about the next block, there would be, for example, somebody who proposes a block, and ideally everyone signs it because they see that it's a valid proposal, and then everyone signs again to say that yes, we all saw that it was a valid proposal. So it's a two-phase commit algorithm, and it uses public-private key pairs to do so, and doesn't use proof-of-work mining. It's also, so Byzantine fault-tolerant means that it can tolerate Byzantine or malicious faults, and it can tolerate up to a third of the malicious signers trying to attack the system. So in other words, as long as there are less than 1/3 of malicious signers, it will continue to function. That's what makes it possible to deploy this in a public setting, similar to Bitcoin. The way Tendermint is created or designed, it is application agnostic. So it doesn't care about what transactions mean. Transactions just appear as binary byte array. In order for Tendermint to know what to do with these transactions, you need to provide a state machine. So the interface between Tendermint and that state machine is called ABCI. It's basically what happens is Tendermint commits a block of transactions, and then it pushes that block to the application state machine and tells it, run these transactions. Of course, there's more details involved, like checktx, which is used to check the validity of a transaction. But the reason why I'm mentioning this is because I want to demonstrate how general the system is. If you look at github.com/tendermint ethermint, That, for example, is a mashup of Go, Ethereum, and Tendermint. So it has Tendermint BFT consensus injected into Go Ethereum, such that you can use the Go Ethereum's RPCs. It appears just like a Go Ethereum system, except there's no proof of work involved. And we can do this because Tendermint doesn't care about the application, and Go Ethereum has all of that logic in there. Basecoin is another application that plugs into Tendermint. It's a cryptocurrency framework that we've developed to make it easy for people to create new kinds of blockchains. So maybe it's a good system if you want to develop a new kind of virtual machine, or if you don't want a virtual machine at all and you just want to hard code some kind of specific logic for your blockchain, then there's a modular plugin system that you can use to develop your cryptocurrency application. The Cosmos hub, which is, well, I'll talk about it more later, is going to be based off of the Basecoin framework. So we are committed to maintaining that as well. So quickly, the properties of Tendermint BFT. Fast finality, so you don't have to wait for additional confirmations of a block because it's a different kind of security model. We've demonstrated a deployment with actually 150 nodes, validators on a global network, and on many data centers around the globe, and we were committing blocks every 3 seconds. So every time there's a block, that block is final. Compare that to Bitcoin, where you have to wait up to an hour, potentially, or more, if the transaction size, the volume is big. It's high throughput, so generally the application logic is the bottleneck. It depends, but it's fairly fast, and because it's regular, that also helps. Like I mentioned, it's fault tolerant. And also, it makes it easy to have fork accountability. And what that means is, when the blockchain forks, so there's a double spend attack, there is a procedure that you can follow to determine who is innocent and who should be slashed. Now, the fault tolerance and fork accountability properties together is what gives it a security guarantee. Because for the system to get double spent, it requires at least 1/3 of the validators or signers to try to attack the system. And because you can find out who they are, it is a system that has some notion of quantifiable security guarantees. And because if you slash them, then it's also a anti-fragile system. It's open source. It exists. We've been release versions, and you can check it out at github.com/Tendermint. And we'd love for you to build on it. There are several projects building on Tendermint today, so come to our Slack channel. That's where we're most active. We have bridges to IRC as well, so don't worry, you don't have to download Slack. A lot of people criticize Tendermint in a proof-of-stake public setting, and they ask, isn't Tendermint too centralized? So that's a great question, because in a classical BFT algorithm, generally, the more signers there are, the slower the system gets. So, for example, I mentioned 100 validators and 3-second block times. But in a non-advanced algorithm or implementation, which is what Tendermint is fairly simple. If you have, say, 10,000 validators, you wouldn't be able to get block commits within under a minute, just because it requires so much cross-communication of signatures. Okay, so 100 validators, isn't that too centralized? Well, I would say that it's not. And the reason why is because if you look at the Bitcoin mining pool, you'll see that the top 20 mining pool operators constitute like 95 or whatever % of the mining power. And we can simulate this. We can kind of create a similar system of delegation, because that's how pools work, right? Anyone can have a mining hardware, but they can delegate to a pool. The pool is essentially controlling what the miner does. We can do the same thing with 100 validators. Those 100 validators become essentially like virtual pools, and we can create a proof-of-stake system on top of Tendermint where you can delegate your voting power their virtual mining power to any of the validators. And I've seen this system self-heal itself whenever it becomes too centralized. People are actually incentivized to move their delegation away from large pools to make a more decentralized system. So I believe this will work. Not only that, but in the future, it's very possible that we'll be able to tolerate, handle much more than 100 validators. So with an exponentially increasing parallel compute power and internet bandwidth and storage capacity, we should be able to tolerate, support an exponentially increasing number of validators. But I don't think we need it. So what is Cosmos about? Like, foundationally, it's about blockchain communication. So the reason why I mention all this Tendermint stuff is because it's the basis for efficient blockchain-to-blockchain communication. And the way it works is what I'm about to describe. If you've heard of proof of existence, it's a similar concept. It's basically the same concept. First, you get a proof of the recent block hash. Okay? So what that is, we call it a commit. What that is it's a block hash along with signatures from more than 2/3 of the voting power of that blockchain, of the validators. And that proves, lots of details are not being mentioned here, but that proves that that block hash was committed. And you can get this within every 3 seconds. And then, so that's the commit of the block hash. And then what you can do is prove anything about that block hash. And because the block hash is Merkle tree, you can prove things like anything about the application state. So any key value in the Ethereum Patricia tree, if you're familiar with the Ethereum Patricia tree. You can also prove anything about the transactions that were included in that block, or any receipt. Or you can prove anything else in the block header, right? So, let's see. So there are, I would say, many kinds, at least 3 kinds of IBC. Something that proves the state value, application state, something that proves the existence of a transaction that was committed, something that proves anything else. Well, I guess those aren't 3 kinds, but those are multiple kinds. I like to split up the tree state key and value proof into 2 kinds, right? So one is a data packet. And this is what the Cosmos white paper starts off with. What you do is you have a packet that is destined for another blockchain. It's much like a TCP or UDP packet. It has a from and a to, and it has a destination, and it has meta information, etc. And you include that packet in the application state in a special key path that says, this is the outbox. Yeah? So you can prove that this blockchain has an outbound packet destined for another chain. Okay? So how do you prove it? I'm just going to go back here. You just need 2 pieces of data. You need the block hash proof, and you need the proof, the Merkle proof of that packet. So now, it doesn't have to be a coin transfer. It can be anything. It could be calling another function in another chain. Basically, it's any kind of outbound packet that you can imagine. It's just a piece of data, much like one computer would send a data packet to another computer. So IBC data packets can be done with or without acknowledgement, similar to how TCP and UDP are with or without acknowledgement. But that's not the only kind of IBC communication. By the way, IBC means inter-blockchain communication. It's a concept. It's not a defined protocol. Like object-oriented programming, OOP, it's just a concept. Another thing you can do is not prove a packet, not prove the existence of a packet, but rather prove the value of some state. Right? So you can prove to another chain that my account balance is so-and-so, or you can prove to the blockchain, destination blockchain, that I have authorized access for this resource. Or it can be about name resolution. It could be about contention lock control. It can be anything. So with Tendermint, because the block commits come so fast, and because they're final, it just makes IBC, inter-blockchain communication, so much easier. So what can we do with this? In Cosmos, what we do is we have a hub. The hub is a blockchain. It's a Tendermint blockchain. It's a proof-of-stake system, and it's a natively multi-asset system. So multi-asset meaning it supports many coins. So it's very similar to what Bitcoin is in the Blockstream sidechain system, except instead of Bitcoin at the center, we have a proof-of-stake multi-asset chain at the center. And all of the surrounding chains, which we call zones, are also Tendermint blockchains, and each zone or sidechain communicates with the hub via IBC. And the hub keeps track of the total amount of coins in each zone such that it preserves the invariance of the total amount of coins issued on the hub system. So the hub doesn't know about the side chains. It doesn't know about the state inside the side chain. It only knows how many coins the side chain has. So in this picture, I've shown the EVM, many EVM zones or Ethereum zones connected to the hub. This is a conceptual demonstration of scaling the Ethereum system. Of course, the Cosmos hub being a token-focused hub, it doesn't support packets, smart contract calls across zones, but you can still scale Ethereum in a certain sense because there are many parallel Ethereum blockchains, and you can move tokens from one chain to another through the hub. So it's not just about scaling, it's also about interoperability. So you can have, so this picture is ambiguous. It can either mean that there are multiple kinds of logic, application logics that are supported in the system. So for example, there might only be one token in this system, but in terms of logic, it might support, this picture supports the Bitcoin UTXO system, well, the Dogecoin doesn't matter, the Ethereum virtual machine, and also a distributed exchange. So these are different kinds of application logics that can be supported by plugging into the Cosmos hub. And now you have interoperability of application logic. But it can also, this picture can also stand for bridging or pegging to multiple existing chains. Pegging is a complex topic. Maybe we can get into it in the Q&A, or we'll try to describe it more in the future. But basically, it's two-way pegging of tokens, for example, two-way pegging of Bitcoins onto the Cosmos hub. So if you bring these different tokens onto the system, you can then move them, transfer them into a distributed exchange zone that specializes in exchanges. So I'm really excited about this use case because the exchange is like a problem that everyone has in the cryptocurrency space. Yeah? Everyone has been affected, or nearly has been affected, that I know, by an exchange hack. And the reason why is because the custody of these tokens is pretty much centralized. Right? But if we have a distributed exchange blockchain that is connected to the hub, that blockchain is distributed. And so the custody of these coins is distributed. And yet, we can actually still support centralized matchers and have distributed custody. So maybe I'll talk more about that. So here's a diagram. I don't know how technical this group is, but it's just an example of IBC, inter-blockchain communication packets happening from zone 1 to the hub to zone 2. You'll see that it's split into two packet types, two data types. but I'll skip it. So going back to the distributed exchange, it's about distributed custody. It can solve the problem that we have today with centralized exchanges. We have a design for a hybrid exchange where even though it's a blockchain and distributed custody, the orders can actually be matched by a central entity. So you can get fast match speeds. So yeah, check out the dex.md markdown file if you're interested. So people might ask, like, why not just use atomic cross-chain transactions? So there are decentralized exchanges that don't require a specialized exchange. The difference is that in atomic cross-chain transactions, you require both parties to the trade to be online for that trade to execute. So you can't set a limit order and turn your computer off and go away, you know, like you can in a centralized exchange. And that means that we will have a more difficult time building an order book in an atomic cross-chain transaction system than with a blockchain where you can set a limit order and walk away for a bit. So that means the Cosmos DEX has a great opportunity to actually build a larger order book and become a more secure distributed exchange system. Now I want to talk a little bit about governance. So Cosmos is really, it's about connecting many sovereign, independent blockchains together. I mean, the Cosmos system will have some blockchains that it supports natively. That so there will be many blockchains supported by the original Genesis Cosmos validator set. But really, what we want to do is connect to many systems and bring them together. And the reason why we want to do that is because every blockchain is a community. They want to be autonomous. They want to have their own sovereignty. They want the ability to even hard fork if they wish. Right? So the way we see a blockchain is we see that there are two parties. The blockchain is, the validators are service providers that provide the service of immutability and uptime, always being up. And then there are the users, the token holders who everyone is trying to service. Now, if you look at the DAO hack of Ethereum, what happened was after the hack, the people tried to figure out what to do, you know, whether to hard fork or not, and how to do so. But there were two problems. So the miners voted, but in proof of work, the miners don't really have anything at stake to stay at one chain. They will go to any chain that will pay them more. The ETH holders were never expected to vote on anything, right? There was no social contract that they had to stick around and vote when an issue comes up. So not many people voted. And so I think the lesson from the DAO in the split of Ethereum and Ethereum Classic is that we need a governance system for a blockchain that says who is responsible for making decisions about this blockchain and how that decision is made. So the Cosmos Hub will also have a governance system, an on-chain system where you can pass a proposal or propose a proposal that can change parameters of the system, but also it will start with a constitution that describes what the blockchain is about and, you know, in human terms, how to react to certain situations and the purpose of the system. And the governance system can also change that through an English proposal. And of course, we will also create off-chain tools to coordinate reorganizations or hard forks in the case that the blockchain should fail. Any blockchain can fail. So a lot of people wonder, like, okay, your system can fail and fork. Well, every system can fail, even Bitcoin. So, for example, if the Bitcoin mining power gets dominated by more than 51%, of somebody who wants to destroy the system, for example, or wants to do things that we all disagree with, we are going to want to hard fork Bitcoin by changing the mining algorithm. So that's the kind of thing we're talking about when we say reorg. Yeah. So the Cosmos, we're having a fundraiser to distribute the staking token, and it's happening soon. So please stay tuned. Please visit the website and subscribe. And I'll take any questions now if there are any. Thank you.
So I would say let's do questions maybe, well, if somebody has a pressing question, we can take one question now. Otherwise, we can, in the end, do a sort of joint Q&A also with Gavin about any questions people have. Okay, then we have Gavin Wood coming up, of course. Most people will be familiar with Gavin. He was one of the key people in making Ethereum happen by writing a beautiful yellow paper that's extremely hard to understand.
Okay. Yeah. Thanks to Jay for the introduction on Cosmos. This is so I'm going to try and explain to you some of the basics of Polkadot here. It may be a little complicated. This talk is kind of more for a kind of technical overview, but hopefully I'll be able to at least give you some degree of education on the basics and the basic idea about what I want it to do. There's basically three things behind Polkadot. The first is this idea of modularity and extensibility. Although existing systems, particularly Ethereum, have made sort of giant strides in terms of modularity by introducing smart contracts, which are effectively protocol extensions, as Christoph Jentsch pointed out. Ultimately, they're still based around a single network, which has its a basic failing in terms of governance, as we saw with the DAO. And I think if we are probably realistic, also the ability to evolve the network going forward. It really does take a lot of political will to push forward consensus networks. Bitcoin is a particularly good example of this, where the protocol has stagnated for many years now with little hope to actually do any meaningful changes to it. The second thing about Polkadot is the ability to scale. So one of the critical things about scalability is to ensure that the single source of security for a network is able to answer for increasing amounts of computation. So while obviously scalability is generally created mostly through parallelizing computation across a distributed set of nodes, it's the ability to secure or have a common founding of security for that computation is, I would argue, critical for that to work. An example here is the Bitcoin sidechains proposal, which actually explicitly mentions this towards the end of the paper, where they point out that there's no, within the protocol itself, no explicit means of scaling the security alongside the transaction throughput that you could have on extra side chains. The final thing is the heterogeneity. So Polkadot attempts to have a number of what I would maybe say disparate chains. So the idea is that you're able to have chains of different varieties. So Jay touched on this in his talk for Cosmos, with the idea of there being differing chains for within the same sort of community, let's say. Ethereum, Bitcoin, and Zcash represent three very particular kinds of chains. I'm sure as we go forward, as this field becomes more and more researched and as more and more people come to it, we will find many different designs of the underlying idea of a distributed Byzantine fault-tolerant state transition system that Bitcoin introduced. So specifically with Polkadot, Polkadot provides really just two things. The first is pool security. The idea behind this is that there can be many different participants, many different stakeholders, but in some sense they all pool their security together, so they all share the same underlying security guarantees and characteristics. This is different to any existing system. It's thus far, security itself is not something that has been managed with an extensible fashion, and this is probably why we all consider the scalability issue to be looming at large with no known, no proven solution. The second thing are trust-free transactions. So Polkadot really aims to allow for arbitrary data in the sense of messages to go between chains. Now, actually, when we talk about transactions, that's really what we're talking about. Transactions really are just a piece of data and a sender and a recipient. So it's just a message, right? Again, Jay mentioned this with the inter-blockchain communication messaging system. And many of those messages that he suggested, so the notion of proving particular state or that a particular coin transfer happened, are relevant within the Polkadot context as well. Polkadot itself works by having a relay chain. So there's a notion of a top-level chain which would coordinate the consensus, all existing chains. So this acts as a global consensus provider. Because it's global, it's able to manage transactions or propagate the transactions between constituent chains. The constituent chains are known as parachains. This is a play on the word parallel because they're parallelized. They can execute things concurrently, but also through the word para, meaning similar or pertaining to, but not quite the same. These are actually the data structures that manage the work. So they collate the transactions and they process them, and it's the relay chain alone which is able to finalize those transactions, or indeed the data that the parachains provide. The relay chain itself has no functionality. So this isn't meant to be a cryptocurrency. This isn't meant to be a smart contract platform. There are no external transactions allowed in general into the relay chain itself. Any fund movement or staking token movement within the relay chain would be transactions that have been injected via a parachain. There may be operations that require fees within the within the relay chain, but this is works according to the decisions of the stakeholders of the relay chain. One of the operations, for example, that may be fee-based would be the addition of a parachain. This brings us on to the idea of governance. So the relay chain itself, as sort of Jay was talking about earlier, its governance itself is very important within a chain, and especially so when you are designing your system to be extensible and forward-thinking. We need means of altering the rules and characteristics of the chain. We also need rules in order to manage the possibility of changes of the protocol of the chain and the addition of parachains in this particular instance. The idea behind the governance of the relay chain is simply to copy more or less what we already know from political science, likely a bicameral sort of system where we have some degree of some technical sort of House of Lords style upper house with some more representative lower house, ultimately reducing to a referendum if there is too much contention between the two. We're slightly, I'm slightly optimistic about this over the real world structures that they're copying, mainly because referendums are not too difficult to organize digitally, but are a right pain in the ass in real life. Here's a basic example of the systems and elements within the Polkadot basic design. The little triangles in the middle are validators. So in a manner fairly similar to what Jay was mentioning earlier regarding a PBFT algorithm such as Tendermint, and the ability to place stake and therefore delegate one's authority to a nominated node. Validators are those nominated nodes. They get the things on the outside here are parachains. They're different colors to denote the different parachain. I've left 4 of them unblurred, so 4 are focused. This one is a bit of an odd one. This one is pretending to be a relay chain as well, and this demonstrates one potential direction for true scalability that we could go in, whereby there is a second order relay chain. So we're able to dive deeper in terms of parallelization and distribution by making a parachain a relay chain, and then the parachains of that second order relay chain potentially could also become relay chains themselves, and so on. The other 3 are kind of interesting. So the Ethereum, the Ethereum logo at the bottom there, this is an idea of like basically a parachain bridge, as it's called. So this is basically where it's not a real parachain. It's not really being hosted by the system, but rather it's a separate chain that has an interface layer that makes it look like a parachain as far as the validators are concerned. It's able to receive and send messages, but how those messages are interpreted by the chain itself, by this in this case Ethereum chain, will depend heavily upon that particular chain's characteristics. For example, a Bitcoin chain may have a very particular data layout in its messages that allow the bridge to interpret the message as a particular kind of Bitcoin transaction. The green one up there at the top gives a slightly more a clear view of what's going on internally within the parachain environment. There are 2 particular entities here, collators and fishermen. The little thing that looks like a J is actually a hook, and they're meant to be fishermen. Collators and fishermen are basically miners. If we want to compare rough sort of job descriptions, they're like the miners of the modern proof of work chains. We can see the red chain is sending a transaction. That's the transaction's coming from a smart contract, a star, and it's going out of the smart contract into the parachain sort of I/O point, and getting through to the other to the green parachain. So if we want to sort of try and understand about who maintains the Polkadot network, then we have really 4 roles. The first are the validators. Validators sit there. They can be nominated by other potential validators, and they're the ones that get moved between parachains they probably get moved between 1 block and maybe 16 blocks. So they may stick around for a little while on a chain, but basically they're very much transient in terms of their role for validating a parachain. And their role is simply to run a function. The function is a single function, validation function. And as a block comes in, it's not a block that has any kind of proof of work or proof of stake, but rather it's a block that has a proof of validity. Now, proof of validity is basically a light client proof that this block is valid, that the transactions have been executed faithfully, and the state has been changed, the message outputs are exactly as they should be, and the validator themselves run the code that allows them to be able to evaluate this. Code specifically is proof of validity function. It's the idea behind the platform that this code would run on is that it runs on WebAssembly. The reason for this is so that one can add new kinds of parachains with new kinds of validation functions without doing any kind of hard fork. Now, I've kind of bundled validators and nominators into a single item here because nominators and validators are kind of more or less the same thing in the network. The only difference is that validators actually bother verifying this. Nominators simply nominate someone else, some other validator or nominator, to verify it for them. And in doing so, effectively trust their stake with that other node. Collators are kind of the miners, if you like, of the individual parachains. They don't get moved around. They commit to a particular parachain, and they actually run a full node for that parachain, right? So they're the ones that actually provide to the validators light client proofs. And in order to create a light client proof, they actually need to be able to execute the transactions based upon the previous block's state. So they actually have to track the state going forward, hence the need for it being a full node. They're able to generate these proof of validity blocks that validators are able to actually determine whether what they say happened in terms of the message throughput and the eventual state route actually did happen. Fishermen are kind of an extra add-on. They don't have much to do. Their main thing is effectively just running a node. The interesting thing that fishermen can do, probably will never do, but can do, is they can work out whether a node or whether a particular block is valid or invalid. Now, if it's valid, everything's working and there's nothing to do. But if they find an invalid block that has been signed by a validator, one or more validators, they're able to report that block as being malicious, essentially. And for that, they're able to collect a fee, potentially a very large fee. In principle, fishermen more closely mirror those who run full nodes on the network without actually doing any mining, so the kind of power users. But in reality, fishermen will probably be be running alongside collators. So when you run a node, you will likely either run it as a validator or nominator, or as a collator / fisherman. There'll probably be two modes. Yeah, I mean, this is just really saying what I've just said. So what's in it for these rules? Why would I bother doing any of this stuff? So with validators and nominators, there's a staking token base expansion. So basically new tokens are minted in order to record who was actually helping maintain the network as opposed to who was just sitting around or wanted the liquidity of their tokens. For collators, there would be parachain specific transaction fees. So they would actually get paid for including the transactions in their particular parachain. Unlike miners, the job of unlike sort of modern day miners, which require to run potentially expensive hardware, potentially power hungry graphics cards, the collators in Polkadot do relatively little. All they do is collate transactions and stick them in a block. So in reality, I think the transaction fees are likely to be, the amount of transactions are likely to be higher, and therefore the total fees are likely to be a little bit more, a little bit higher than we see in Bitcoin or Ethereum, but perhaps probably still roughly equivalent to the power that they would otherwise spend. Fishermen get, as I said, a potential gift as the proportion of the bond for the culprit that they identify. And if they're identifying a validator that's very well bonded, then that could be a very significant amount. In terms of forming the consensus, there's this notion of a proof of stake algorithm that the relay chain runs as it provides consensus for all of the constituent parachains. Now this basically guarantees shared canonicality or shared finality across all of the system. Now, this is important because if a message arrives from one parachain into another and has significant side effects, or indeed any side effects at all, since we can never tell what significant really means, then we have to commit to either both or neither. We can't say one cannot revert what it wants to do. As such, there's a single canonicalization algorithm, and that's what this is. Secondly, there's a structured state machine. It's likely to be a PBFT derivative with particular augmentations for managing the parallelized consensus of the individual parachains. Since the validators get split up into subgroups, one group for each parachain, it would be nicer if they can parallelize their efforts to form consensus over which of a potentially large or potentially several block candidates for those parachains will be the winner and will be the one that is determined to be final. Yeah, and that basically is how Polkadot manages scaling. So scaling, for what it's worth, is effectively the ability to split two key functions of a blockchain from each other. So blockchains do two things. The first thing they do is they validate transactions. You have to ensure that the transaction and potentially any state route or message output that a blockchain does is valid. If it's not valid, it's not doing its job. The second thing a blockchain does is it must commit to one of a potentially large number of candidate transactions rather than include mutually exclusive transactions. For example, if I have 100 Bitcoin in my account and I send 100 Bitcoin to John and 100 Bitcoin to Dave, it's very important that unless I receive another 100 Bitcoin in the meantime, only one of those transactions is mined, right, is finalized. If they're both finalized, there's something wrong. So this is what blockchains do. Now the problem is that while canonicalization or finalization is relatively easy to do on scale, validation is not. Validation really does need to be parallelized. But unfortunately, canonicalization cannot be parallelized. It's necessarily a serialized process because you have to actually finalize everything or nothing. You can't finalize little bits at a time if they depend on each other. So what we do is we split these two things up. We first do the distributed processing, which is to say the validation of transactions. And then secondly, once we're happy that the transactions have been validated, we canonicalize or finalize everything all at the same time. And that's really when I talk about Polkadot, that's really what Polkadot is doing. There's very little additionally. Okay, so validators and nominators. Effectively, you have a pool of participants, which may be validators or may be nominators. We have this notion of approval voting. So approval voting is basically where there are a number of candidate options, and I'm allowed to tick as many of those boxes as I want. I can tick just one box if I only approve of one candidate, and that's very similar to how basic voting systems like the UK's voting system work. I can choose a winner, but that's all I can choose. I might tick all of the boxes apart from one, in which case I basically don't care who wins as long as it's not one particular candidate. I may tick a number of boxes and not others, in which case I maybe have a more balanced approach. Well, this is how this validators and nominators, and particularly the nomination of a validator works. As a nominator, I place some stake, and I'm able to tick a number of boxes as to which of the participants should be able to take my stake, my bond, my deposit, and validate blocks for it. Now this might include me, it might not include me, it depends. Maybe I don't want to be a validator myself. Maybe I'm happy if Etherpool, or the people who run Etherpool, and the Interchain Foundation do my validation. But I don't want to do it myself. It depends. The second thing is a constraint optimizer. So given all of these all of these votes in the approval voting mechanism, and also given a number of bits of other information, such as the amount that I want to stake and how much I want to stake it for. It may be that I'm happy to do the staking for a 5% annualized return, but I'm unhappy if it's less than 5, if it's only 2%. Now this information gets fed into the constraint optimizer, and the constraint optimizer is able to give basically a minimum if we take the total inflation required, a minimally total inflation, minimal inflating currency, or token base, with the maximum amount of lowest bonded validators. So basically, we want as many people as possible, as higher bonds as possible, but rather than having, one participant has got 1 million tokens and the others have got like 10 each, we want to take the lowest bonded participant and maximize the amount of bonds that they have behind them, since we actually this will end up being the bottleneck, or the target of security. And finally, we get the adaptive rewards, which basically you're able to target the amount that you want back, which allows us to minimize introduce a market mechanism to minimize the amount of total inflation that the token base will undergo. So now if we talk about how parachains themselves are validated, we have the idea of collator candidates. This is effectively where multiple candidates are sitting around in a parachain ecosystem. They all want to provide their blocks. They only get paid effectively with the transaction fees if it's their blocks that get determined to be the ones that should be canonicalized or should be finalized. And so they come with this idea of proof of validity and also some external data, which is to say the transactions that have been introduced into that particular parachain environment that want to be mined, sort of finalized or whatever. Now we have these two distinct things. The first is availability, and the second is validity. Now these are two attributes that are given to collator blocks. Availability is effectively, does the data that this particular candidate block depend on, is that data available? Can I see it, right? If we can't see the transactions that come into a parachain block, then it becomes very difficult, well actually impossible, to know whether those transactions have been executed correctly, because we can't execute them ourselves. Now the second thing is validity. Even assuming I can see what those transactions are, I am able to execute them, are they actually valid? So do they end up with whatever state transition is meant to be done? Is it a valid state transition? And basically, you need to be able to vote on whether something is available and something is valid. The blocks themselves, only the validators who are assigned to this particular parachain are able to vote on validity, because of course it's only those validators that are actually executing anything. The others are busy with their own parachains. But ultimately they can all vote on whether they can see the data that's available as it floats around on the network. In terms of relaying transactions, this is probably the most complex part of it. Essentially, we have a need to be able to transmit data between validators as they operate on different parachains. So, as a transaction leaves one particular parachain and needs to arrive at another parachain one block later, we need to arrange that delivery. And of course, we need to ensure that it's it's trustworthy, or that it is the data that left, which is non-trivial given that the validators each operate on different chains and otherwise don't really see each other. Of course, the way to manage it is to use cryptography, and we use Merkle trees in order that we can provide proofs that a particular bit of data that exited a parachain on block N is the same bit of data that arrived at another parachain on block N+1. And these Merkle, the roots of these Merkle trees, and thus the basis on which the proofs are given, are recorded into the relay chain, which all of the validators have access to, regardless of which parachain they're assigned to. This allows us to create proofs of misbehavior in the case that a validator is placing an invalid message in the queue of another parachain. So the next thing to think about is availability. How do we ensure that the transactions and the various bits of data that we need are available throughout the system as they need to be available? This boils down to a second problem, which is to ensure that that collators who are the ones that really need the data to be available, are chosen from a fair set. So basically, we want at least one active collator per parachain that is that is able to keep up with the data and is able to check to see if the data really is available. As long as we have one of them, then they can flag when data isn't available, and we can go to the validators that signed that it was available and take them to court, basically to take their bond off them. But it's super important that we do have that one collator. So how do we ensure that it's worth it, that there is that one collator always hanging around? Effectively, what we do is we manage we invent the notion of a golden ticket. And the golden ticket is basically a randomly chosen address, it's formed through some pseudo-random, but cryptographically pseudo-random deterministic process, such as block hashes or signature hashes. And we say that whichever collator whose address, when they sign the block, the candidate block and submit it, whichever collator has an address that is closest to this randomly selected address wins, sort of like a lottery. What it does is it ensures that small-time collators, even those with maybe less good bandwidth, are able still to get blocks inserted in the main relay chain. Now, once we can validate that a collator's address is actually inserted, we now have a set of participants who are in some sense stakeholders in the system that we can prove very easily, because they just say, hey, I had a block in the last 10,000, sure, it was this block and here's the proof. We are now able to basically give these guys a responsibility and an authority to provide a policing behavior for when data is not available. And when data isn't available, we can give validators potentially a punishment, or maybe just a reduction of reward if they sign blocks that are not available. Okay, so that's basically the entire protocol. The only other thing to mention is this idea of how it interacts with consortium chains. So consortium chains, or internal chains, or private chains, if you're not familiar, basically it's this sort of intranet version of a blockchain where it just sort of sits behind closed doors and it manages whatever things that businesses want their blockchain to manage. Now, this is kind of quite similar to the whole intranet-internet duality, in the sort of early to mid-90s, where companies were like, oh, well, we don't want to go on the internet. There's no point doing that. It's just a security issue. But we kind of like the idea of being able to share documents between computers within our particular company network. Of course, the internet revolutionized everything, so they were kind of wrong, but short-sighted, if not. They had at least some particular efficiency gains during those first few years of TCP/IP. The same is true with blockchain. And if you go out to enterprises and industry, they kind of say the same thing. Oh, well, public chains, no, we don't really want any of that. But we are kind of interested in deploying a private chain so we can muck around with it. Okay, fair enough. One of the nice things with Polkadot is that they can do this, but yet they can still plug it into the sort of internet of blockchains, as it were, through a potentially sort of either bridge system if they have their own consensus mechanism, or if they use something similar to Polkadot's consensus mechanism, that could potentially be a parachain, but where they have, rather than the entirety of the transactions being validated by validators which they may not know or care to give the internals of their transactions to, they could be validated instead by just simply checking whether the validators or the sub-validators, if you like, of their own network, on their own like proof of authority network, are happy to sign off on the block. So effectively what we can do is have validators of the Polkadot network be sort of subordinate to the validators of a consortium chain. And in that sense, the consortium chain can keep its transactions private. It can keep sovereignty over even the finality of the blocks, and certainly over the ability for transactions to be executed, without any issues of having everything private and therefore unable to interoperate with the rest of the world. In principle, this could bridge them into Ethereum, Bitcoin, or whatever. Okay, I think that's it. Yes. That was probably about as clear as mud, but if you have any questions, yeah, I guess we can probably do a shared Q&A session now. Yes, Fabian. Would you like the mic?
How do you deal with finality? So how you make sure that basically like if you wait 12 blocks to collate waits like a specific amount of blocks before he propagates or generates the proof or the
Okay. So this is a question on finality. Effectively, finality is guaranteed by the validators of the relay chain. So the relay chain guarantees finality for everything in the system. So it acts kind of like the finalizer. Now it uses, at the moment, the basic assumption is it uses a PBFT-derived algorithm, probably, possibly like Tendermint, from a derivative thereof, which has a nice characteristic of giving finality within one block. So basically once, whatever, 66% of the validators have signed off, assuming you haven't got some ridiculous amount of Byzantine nodes in your system, that's it, it's final. And if you have, then you've got to do something way out of band anyway, so you may as well. Right, so the parachains provide, so the collators of the parachains, generally there'll be a few of them, they'll all sort of try and provide their block, right? They'll kind of mine a block with this proof of validity, like client proof. And it's up to the validators, to work out which one of these candidate blocks they will decide, crown as winner. Once they've crowned one as winner, that's it, it's the winner, right? There's no going back because we are finalizing it under this one block finalizing proof of stake system. Mm-hmm. Yeah, so the point of the relay chain validators is to ensure that all parachain candidates, or one of each parachain candidates, I should say, is finalized at the same time. And therefore, the parachains do not have the ability to provide, to reorganize themselves. They do not have that level of sovereignty over finalization. They give that up to the relay chain. So that's how we guarantee that there can be no reorganization of one parachain without a similar reorganization of another parachain. Which isn't to say that reorganizations kind of in theory can't happen. We've sort of got some models for how we could reorganize all chains in the case of a massive Byzantine problem on the relay chain. But if that were to happen, then the protocol would ensure that all of the parachains were indeed reverted. Does that help?
So my main question is like really like what I don't really get yet is decide on the parachain. Like how is ensured like that there's not a state or like a truth like discrepancy creating at some point if there's like a fork happening in one blockchain, which is a parachain, but then there's something already sent out as valid in the relay chain. Like I don't really understand 100% that.
Okay, so a fork is a fork in finalization. Yeah. So when sure, but a fork in general is a fork of finalization. So it's where you go in one direction and you think you've been finalized, but then actually you go back and you go in some other direction. Yeah. Okay, so the act of finalizing is not an act that a parachain can do. It is simply unable to finalize. It cannot finalize if it wants to finalize. Rather, finalization happens only by the relay chain. So the relay chain basically gets the point to which fork, potential fork, wins. Right? Well, the parachain, the collators of the parachain actually maintain a light client of the relay chain. So they're able to check to see which of their blocks got chosen and sync accordingly. So from their point of view, the thing that chooses the winner isn't like their own particular parachain, but rather the relay chain that they submit their candidates to. So they basically, as far as they're concerned, they submit a candidate to the relay chain validators. They do something, and then a couple seconds later it says, right, we chose this one. And once they say, right, we chose this one, they know for sure, the parachain guys, the collators know for sure that there's no going back. Because it's got all the signatures from the PBFT, Tendermint, whatever algorithm. Okay.
So loud. So you described that you have the abstract blockchain interface and you can put a generalized application on top of it. My question is, because I don't think there's code for Cosmos public yet, right? Or I've not looked at it yet. Is the Cosmos hub written as an application on top of the ABCI, or is it a dedicated interface that you're looking at? And is it then possible the same way that you can run multiple applications on top of the APCI, that you would run the hub next to your own zone so that you get a tree network of hubs? Yeah, just small technical questions. Thanks.
Yes, to your first one. I really like abstract blockchain interface. That's probably what we should stick to. ABCI, but we were always trying to figure out what the ABCI actually mean. Yeah, so if you look at Tendermint, github.com/tendermint/basecoin, that's the cryptocurrency framework we're developing in Golang, and that exists. We're actively working on it, and that is what will become the Cosmos Hub, and it is an ABCI application. I'm not sure what the second question was. Were you asking whether one Tendermint process can have multiple ABCI apps running simultaneously? So like hierarchical, recursive. Yeah. I'm not sure if that's going to happen anytime soon, but certainly it can. So one way in which this might happen is if it turns out that that the global internet, availability is not good enough, we might want to have multiple hubs in every continent, say, and merge those by having a top-level hub, but have regional hubs as well. So that can happen, and certainly coins can be transferred like that. I think that makes quite a bit of sense. I just don't know if that's what we should focus on at first. Yeah, but I think eventually it has to go that way because that's the only way to maintain availability in the presence of a global partition.
Yeah, so let's do, we can do 2 more questions.
Hello, thank you for both talks. They're very similar in a high-level interface, and I was interested in the hub or the relay node and the Cosmos chains and the parachains, and in how they communicate. They have to communicate in a non-blocking way. And you mentioned, Gavin, that when a parachain commits on block n, it has to arrive block n+1 on the other parachain. And how that's done, communicating between the parachains in a non-blocking way without blocking consensus if the network is slow. Also the same with J, how the IBC handles the communication between the 2 nodes in a non-blocking way.
Yeah, it's not an easy problem to solve. The design of Polkadot basically manages this through firstly pre-reserving or pre-connecting between nodes. So it's possible to see up front which the next 2 or 3 blocks, which validators, will be sitting on which parachains to validate them. This is the second reason. So basically, you can have the connections that you need, the conduits that you need open at the time of needing them. So you don't need to do that TCP/IP handshake in order to do that, which reduces some of the latency. The second point is that the validators are able, the collators are able to, they're incentivized to ensure that the collators on the other side, for the other blockchain, have the information, because those are the ones that will, have the information for the data coming in, because those are the ones that will basically be able to be building on that data. If they can't build on it, then they won't be able to produce additional blocks. Similarly, they're incentivized to ensure that the validators, that those second block collators will be pushing their candidates to have the information so that they can do the proof of availability and proof of validity and sign off basically that the data is indeed available. So they will seek to actually connect to the validators on the next block and push the data out to them in order that it makes it more likely that their block will be voted to be to have all information required available. So although we can't guarantee that the network will be fast enough to ensure whatever 4-second block times, what we can at least do is incentivize the relevant parties and give them the ability, give them knowledge about where they will have to push their data to on a peer-to-peer basis to maximize the chance that they will actually the data will be where it needs to be when it needs to be. If there is a big kind of global network outage and it just turns out that the validators cannot connect to each other, effectively what you'll end up with is that some particular combination of parachains will simply have no blocks for a period of time until the connectivity restarts, and as such there'll be probably some largely arbitrary or randomly chosen number of validators and collators that will get a bit have their rewards reduced for that period of time. But that said, you know, you don't become a validator if your internet connection is sketchy. You know, part of being a validator, and the reason, and this is maximized by the fact that actually there aren't probably going to be all that many validators, maybe 1,000. You would become a validator partly because you have very good connectivity and uptime as well, obviously.
So in Cosmos, in the hub, the IBC token transfer transaction from, say, a zone or a sidechain to the hub, and then another packet from the hub to another zone. This can happen completely asynchronously. So it doesn't matter how long it takes, really, because as long as the packet still needs to get acknowledged, it will stay in the state in the outbox until an acknowledgement comes. There's some timeouts issues here that I'm glossing over, but it's not a synchronous system. So it can, if there, for example, if there are way many zones connected to the Cosmos hub, you can imagine that not everyone will be able to commit an IBC packet or coin packet to the hub in time, but that's okay because everything is happening asynchronously.
Okay, last one.
So you have two interesting projects here, which obviously have their own trajectories, and it seems like you're also kind of tying things. And this is maybe an organizational question. You are also tying these things together via the Interchain Foundation, but theoretically, what is possible in terms of interoperability between these two projects? I'm not asking you to commit to anything firm at this point. Obviously, things are still very early. But what could we be looking forward to in that respect?
So Jay and I talked about this a while ago, last year. So from my point of view, I think firstly, there's some degree of baseline interoperability possible through standardization process. In particular, trying to manage the format of messages, cross-chain messages, so that both systems use the same underlying formats. In terms of actual connectivity, I think that realistically, we're probably looking at either a bridge mechanism, which is similar to how on Polkadot's side it connects to Ethereum, and probably will be similar to how on Cosmos's side it would connect to Bitcoin on Ethereum as well. This would allow tokens to float between each network, or kind of on a more hierarchical level, it may be possible also to have the Cosmos network actually appear as a parachain within the Ethereum. Within the Polkadot. Oops. Within the Polkadot community. One other possibility that is worth considering is that the relay chain of Polkadot is a zone within a larger hub of the Cosmos system as well.
Yeah, we haven't decided exactly how that's going to happen. But I am committed to making them interoperate. I'm sure we can make that happen. So whatever is sensible, I'm sure we'll come to agreement on.
Right, well, thanks so much. So thanks so much, everybody, for coming. Hopefully this will have turned out, in retrospect, have been a historic event. Well, we'll see. So we are sort of on our way out now. There are some pizzas there. Some people may not be aware of it, but have a slice or two. But I think we're also going to have to basically kind of get out of here maybe in 10, 15 minutes or something like that. So, although, yeah. So thanks so much for coming.